Hi everyone, it's Miss Coletta here, and today we're going to look at the binomial theorem. The binomial theorem is another thing that's helpful in doing expansions of products to some power. So we've already looked at how Pascal's triangle can help us do these things. We've talked about how Pascal's triangle can help us find specific coefficients. We've talked about how we can identify terms that have the same coefficient based on the symmetry in Pascal's triangle. And we've looked a little bit at expansions of binomial products, but we're going to look at the whole expansion again using binomial theorem. So here are the main ideas behind binomial theorem. When we're doing an expansion of a plus b to the n, there are n terms, a plus b times a plus b times a plus b, n times that we're multiplying together. So since we're always multiplying n items together, the exponents on the a and the b terms will always add up to n depending on which ones you chose to multiply together. We can use that combinations pattern then to find the coefficients. And in terms of the exponents, we'll always organize it so that a goes from the largest possible exponent, n, down to the smallest, 0, and b will go opposite, from the smallest to the largest. So let's just take a look at some of the patterns we're going to see, and then we'll go into some examples to help demonstrate this. So for the patterns, the coefficients will begin at n choose 0 and end at n choose n. And this would be the same as using what row of Pascal's triangle? Does anyone know what row n choose 0 and n choose n would both come from? That's going to be row n of Pascal's triangle. So if you would prefer to use that, you'll see later in the examples, you can skip the step of using the combinations, the n choose 0 and the n choose 1 and the n choose 2, etc., all the way up to n, and you could just use row n of Pascal's triangle. So that's a choice you can make. The exponents on the a term, we said just for organization's sake, we're going to start those at the highest power and go down to the lowest. And b will go backwards then. It will start at 0 and go up to n. And together, as we said, the exponents will always add up to n, which you can probably see here with a having an exponent of n and b having an exponent of 0. Those would add up to n. Same thing at the end here, a having an exponent of 0, b having an exponent of n would add up to n. And in between, if a is counting down and b is counting up, again, we'd have them add up to n. So let's look at the actual formula for the binomial theorem. If you are expanding a plus b to the nth power, it would look something like this. We would start with the coefficient n choose 0, as we said, and a would start with the largest exponent, b would start with the smallest. That would all be one term. Then the next term would have a new coefficient, n choose 1. A's exponent would go down 1, so instead of n, it'd be n minus 1. And b's exponent would go up 1, so instead of 0, it'd be 1. We'd keep going here. And eventually towards the end here, we would have n choose n minus 1. That would be the second to last term because we haven't quite counted up to n. A's exponent would be all the way down to 1. B's would be all the way up to almost n minus 1. And the final term, n choose n. At this point, a would be all the way down to 0, and b would be all the way up to n. So that's the formula for the binomial theorem. Now, there's a little note down here at the bottom about Pascal's triangle. Don't forget that you can use Pascal's triangle to do the expansions too. You would use the numbers from row n of Pascal's triangle as the coefficients, and then you'd follow this same pattern for the exponents. And when we work through the examples, I'll show you how you can skip over doing these actual combinations here, the n choose 0, n choose 1, if you would prefer, and you can use that row of Pascal's triangle instead. So without further ado, let's jump right into the examples. Okay, so our first example here is a general example. You can see we're still just doing an expansion of a plus b to, in this case, the fourth power. And later on, we'll add in actual variables and numbers here and see how it makes the process a little bit different. So starting here, I'm doing the expansion of a plus b to the fourth. And looking at the binomial theorem, I know that I need to start with n choose 0, but in this case, n is the power 4, so we'll be doing 4 choose 0. And remember, the a starts with the highest possible exponent, which is 4, and the b starts with the lowest, 0. So that's my first term. Then I put my plus sign before my next term, and now my coefficient would be 4 choose 1. The a is going to count down 1 from 4 to 3. The b will count up from 0 to 1. And we'll continue. The a will count down to 2, the b will count up to 2, and so on. Hopefully this pattern is semi-familiar to you from when we did it a little bit with Pascal's triangle. Now a is all the way down to 0, b is up to 4, and that's when we know we're done, when we've reached that n choose n, and also when our exponents have switched so that a is down to 0 and b is up to 4. Okay, so now we just need to clean up this example a little bit. So the first thing I'm going to clean up are the coefficients. And if you remember, we can type in combinations into our calculator. The notation's a little bit different. We would say 4 NCR 0, but that's what we're going to do on our calculator. So let's just take a look. The first thing we would do is type in the 4, if you remember, and then we would hit the math button to find that NCR option. Now you need to arrow over until you're on the probability menu, but once you're on probability, you would select option 3, NCR. And then you want to do 4 NCR 0, so you would just type that and hit enter. And we could continue for our other coefficients. 4 NCR 1, 4 NCR 2, and so on. Now, I'm going to write these in, and I'm going to talk a little bit about how we could use Pascal's triangle instead of combinations if you would prefer. So hopping back to our screen here, I know that 4 NCR 0 simplifies to just 1, so I'm going to replace that with a 1, and this is a to the 4th, b to the 0. Then I'll continue. 4 NCR 1 became 4, and this is a cubed, b to the 1st. Notice that I'm not simplifying the actual exponents on the a and b terms yet. I'm going to save that for the next line, and I'll show you why. This simplified to a 6, a squared b squared, and then I would continue here. And hopefully maybe you recognize these numbers from Pascal's triangle. This 1, 4, 6, and maybe you know where they're headed. But what I want to show you is that instead of using combinations, you could actually use Pascal's triangle from the get-go to get these coefficients. So to use Pascal's triangle, I would just start writing it out. I know that the first row is just 1, and that's row 0, really. Then row 1 is 1, 1. Row 2 is 1, 2, 1. Row 3, you might remember, is 1, 3, 3, 1. And row 4 is 1, 4, 6, 4, 1. So we would actually use this row, because we're doing the expansion a plus b to the 4th, and those would be our coefficients. So you would see here then that we are actually going to have 1, 4, 6, and then the next two would be 4 and 1. So if you wanted to just use Pascal's triangle to find those coefficients, you wouldn't have to bother with the combinations in the calculator. But whatever works the best for you is absolutely fine. So using that 4 and the 1 that I know I'm going to get at the end here, this becomes my expansion. And if you were going to use Pascal's triangle, you could start right at this line of work. So now we're going to simplify the individual terms. So 1 a to the 4th, b to the 0. Do you see anything that simplifies here? That's right, the b to the 0 would become just 1. So think about what we're doing here. We're multiplying 1 times a to the 4th times 1. So really, at the end of the day, don't we just have a to the 4th? Plus, and now we'll do the next term. Now, this 4 times a cubed times b to the 1st b to the first, I don't really need to write that first power, so I can just write 4a cubed b. And we'll continue. 6a squared b squared. Nothing really cleans up there. 4ab cubed, I don't really need to write the power 1. And then, again, this a to the 0 would become 1. So I have 1 times b to the 4th. That's just a plain old b to the 4th. And for this example, I am done. Now we'll see that when we do this with numerical values in for b, that there will be a little bit more simplification to do than this. But for this example, that's it. That's our expansion. Okay, so we're going to move on to the next example, and notice here that instead of a plus b to some power, we have x plus 2. So things are going to be a little bit different. There's going to be an extra step that we'll need to do. But I'm going to go ahead and get myself set up here. X plus 2 to the 5th equals. And now we know that we will either use the combinations from 5 choose 0 to 5 choose 5, or we'll use row 5 of Pascal's triangle. So I'm just going to write out the combinations here so that you can see them. But again, if you use Pascal's triangle, then you might skip this line and go on to the next line. So I know I'll start with 5 choose 0, and then I would do a to the 5th. But take a look here at this example. Where we used to have a, we're now going to have an x. So instead of a to the 5th, it's going to be x to the 5th. So we put x to the 5th. And where we used to have b, we now have a 2. So I'm going to put 2 to the 0. And that's the only thing that's going to change at this step. We'll deal with the simplification when we get there. Now the next one will be 5 choose 1. And the a, in this case the x, will count down to 4. And the b, in this case the 2, will count up to 1. And continue on. So hopefully this is not a huge leap for us. 5 choose 2. The x counts down. The 2 counts up. The x counts down. The 2 counts up. And the last one, you can see you get kind of tight on space with these because they can be kind of long. So you have to try to space it out okay. There we go. Now we're going to simplify this line, or if you were using Pascal's triangle, you would just start at this line. So 5 choose 0 is the same as row 5 of Pascal's triangle. If I go back up to my red Pascal's triangle here, then I could add row 5, which would be 1, 5, 10, 10, 5, 1. So this is going to be the one that we're using this time. Okay, so I can put those in place of the combinations. So this will be 1 x to the 5th times 2 to the 0 plus 5 x to the 4th times 2 to the 1 plus 10 x cubed 2 squared plus 10 x squared times 2 cubed plus 5 x to the 1 times 2 to the 4th plus 1 x to the 0, 2 to the 5th. Okay, and now we can go ahead and simplify. Now here's how things are a little bit different. Up top, when we were doing these ones, a to the 4th, b to the 0, well the b to the 0 just went away. That was fine. Then when it was b to the 1, you still had a b term here. However, when you look down here, that 2 to the 0 will go away because it'll be 1. But 2 to the 1, that's going to be 2. So that's another number to actually multiply in with my coefficients. So what I'm going to do is I'm going to simplify all the numbers across and then have the variable. And notice the only letter that's left is x. So here I have 1 times x to the 5th times 2 to the 0, which is really 1. So that's 1 times x to the 5th times 1. That's just 1x to the 5th, which we'll just write as x to the 5th. Here, though, 5 times x to the 4th times 2 to the 1st. Well, I'm going to put the numbers together. 5 times 2 to the 1st, 5 times 2, that's 10. And then this is x to the 4th. Now here, the numbers 10 and 2 squared. So if I were going to go on my calculator there, let me just show you how I would type it in. I know these numbers are small enough that we could do it, but just so you see. So I would just type 10 times 2 squared and get that coefficient of 40. And then I'll continue to do that where I type in just the numbers and simplify everything step by step. Now 10 times 2 cubed will give me 80. 5 times 2 to the 4th will also give me 80. And x to the 1 is just x. And then 1 times 2 to the 5th will give me 32. And x to the 0 is just 1, so we actually don't have an x in that term. So when you look across here, it looks a lot different than the last problem we did. That x to the 5th is pretty similar, but then here, notice you don't have any second variable because it was replaced with a number. That number gets absorbed into the coefficient. So the coefficients have actually changed just because the b term was a number. So you might notice that that symmetry has kind of disappeared from our answers here, and that's okay. That doesn't mean we've done anything wrong. It just means that because we're using both numbers and letters in doing our calculations, that they're going to simplify differently and it might not be perfectly symmetric. Okay, so it's time for our last example here. So let's take a look here. The nice thing about this one is that we're only expanding 3x minus 1 to the 3rd power. So the smaller the power, the easier it's going to be, just because it'll be shorter. Now, notice though, we have 3x and we have a negative 1. So there's some things we're going to have to be careful about here as we expand. So let's go ahead and get ourselves started. So I'm doing 3x minus 1 to the 3rd power. And now we know that we'll either use the combinations 3 choose 0 through 3 choose 3, or row 3 of Pascal's triangle. As always, I'm going to write the combinations out just in case you're using the binomial theorem, but if you're using Pascal's triangle, then that's okay too. Now notice here that my a term is a 3x. So instead of a cubed, I'm going to write 3x, the quantity cubed. Now remember that I mentioned that we have a negative 1. That's because when I look at this 3x minus 1, it's usually a plus b. So what are we really adding here? A negative 1. And remember, we always just look to the left of a number for its sign. So here I'm using a negative 1 as my b. In this particular part, it doesn't really matter because we're raising it to the 0 power, but it will later. Now we'll keep going. 3 choose 1. 3x counts down to squared. The negative 1 comes to the 1st power. And then continue, last one, 3 choose 3. The 3x, the quantity, is now to the 0. That's our signal that we're done, and the negative 1 is all the way up to 3. So now we're ready to simplify. I'm just going to simplify the coefficients, so again this would be the same as your first step if you were just using Pascal's triangle. Row 3 of Pascal's triangle is 1, 3, 3, 1. So those are the numbers I know are going to replace my combinations. So this is going to be a 1 times 3x cubed times negative 1 to the 0 plus 3 times 3x squared times negative 1 to the 1 plus 3 plus 1 Now here comes the trickiest part when we go to simplify, and I'm just going to show you the first term and then I'll let you do it for the rest and then you can check and see how you did. So looking at this one, I have 1 times 3x the quantity cubed times negative 1 to the 0 power. So what I'm going to do is I'm going to simplify all the numbers just like I did before, but instead of just having the 1 here and the other number negative 1 here, this is a 3x. So that 3 is going to get affected and brought in as part of the coefficient too. Now, do you know if 3x, the quantity, is cubed, what we have to do to each of these terms? That's right, we actually have to cube both of them. So this is going to be 3 cubed and x cubed. And this is the part that students typically forget, is to cube both pieces. So what I do is, again, I do all the numbers all across first. So I'm going to do 1 times 3 cubed times negative 1 to the 0. Simplify all that stuff. And then after that, I'll put the x's. So let's just hop to the calculator real quick so I can show you how I would type that. So I'm going to do the 1 times 3 cubed. And my exponents might look a little different than yours just because of my calculator. But I use the caret to get the exponent, times. And then when I put that negative 1, I need to put it in parentheses. And it's to the 0 power. Which we know is going to just make it kind of go to 1, but that'll help us simplify it. So then the number that I need to use here is just 27. So that will take the place of the first term's coefficient. So this all together becomes 27, and now I need to put my x. It's x to the 3rd power. And that takes care of that whole term, because I've taken care of the 1, I've taken care of the 3 cubed, and I've taken care of the negative 1. And now we'll continue that. So this one would be 3 times what? 3 squared, and negative 1 in parentheses just to the 1st power. So go ahead and see how you do it simplifying the next term. Okay, hopefully at this point you've simplified just this term, and you've seen that you came out with a negative. You should have gotten negative 27. So what I do is I actually adjust this part as I go along. So if I get a negative number out, then instead of having a plus sign, I'm going to get rid of that plus sign, and I'm going to put a minus sign. I'm going to put minus 27, because I know it was a negative 27. And then that way I've taken care of the sign, and I don't have to worry about having two signs going on at once. And this is x squared. Now I'll take a minute and try the next term. Did you get 9x? Here in the numbers, 3 times 3 to the 1 times negative 1 squared. Now negative 1 squared comes back out to a positive, so it stays as a plus 9x. So go ahead and get your last term simplified, and we'll see how you did. Hopefully here you got minus 1. And this one's weird because you see this 3 and think there's going to be a 3 involved, but look, 1 times 3 to the 0 power, well that's just another 1, times negative 1 cubed, well that's a negative 1. So it comes out as a negative 1. And then you would have x to the 0, but what's that? Oh, that's just 1, so that would go away as well. So this would be our final answer. At this point we've simplified this binomial expansion and we're done. Thanks for joining me, guys. I hope this helped you with binomial theorem.